So when we last left off, we were discussing the Iupac method for assigning the configuration for each chiral center. So remember, our first order of business is to order our groups in order of increasing priority. Then, once we have our groups ordered, we place the lowest priority group in the back, and we look and determine whether counting from the highest to lowest priority, so priority 1 to priority 3. If we're dealing with a clockwise rotation, then it's R. If we're dealing with a counterclockwise rotation, then the configuration will be S. So what I want everyone to do is to try to assign the center for the following chiral center in this molecule. This is a variant of an amino acid, which may be a hint as to probably what the stereochemistry would be at that stereocenter. But let's utilize the Iupac method and let's try to assign the configuration at that stereocenter. And we'll discuss this example in about 2 to 3 minutes. And I'd like to see students share in the chat their proposed stereochemistry. And in addition to that, ideally, I'd like to see students as well share their priority numbering using the annotate tool. And we'll discuss this example in about 2 to 3 minutes. But really importantly, rather than, I'd like to see the reasoning behind your answer. I'd like to see the actual numbering method that you use, and I'd like to see your priority group assignments. And I recommend, as I'm doing right now, putting together a model of this structure. And we'll discuss this example in about 2 to 3 minutes. And don't be shy to share any questions you have in the chat, as well as your proposed stereochemistry assignments in the chat. And just as a reminder, you can use the annotate tool at any time to write out your group priority numbers and assign priority to each of the groups for this molecule. And let's try to get some assigned configurations in the chat. So in order to use the Iupac method, your molecule first needs to be rotated so that the lowest priority group is in the back. So from your assignment, your priority numbering is correct. But what I'd like you to try and do is rotate your molecule so that the hydrogen, which is the lowest priority group, is in the back. But you're on the right track. It's just a matter of rewriting and rotating the molecule. And once you've rotated your molecule, so the hydrogen's in the back, then you're able to assign priority with no issues. Try to give it a shot rewriting this molecule. And that proposed priority assignment and the proposed stereochemistry assignment was on the right track. The only thing to keep in mind is that the hydrogen, which is the lowest priority group, should be in the back. So in this case, we see that the molecule was rotated so that the hydrogen's in the back, and from highest to lowest priority, the configuration was assigned as S. This looks reasonable so far, so let's talk about this and let's use a model. So here is the model for our molecule. Let's just focus on the amino acid portion. Let's focus on, so here's the model. Let's just focus on the amino acid portion, the stereocenter. As we see, our hydrogen's in the front and our amine is in the back. So what I'm going to do is I'm going to rotate my molecule. And set it up so now my hydrogen's in the back. So I'm just going to draw what I see here. So now I have my amine in the front, and this carboxylic acid is pointing, oh, whoops, sorry. I'm so used to mirror images. So drawing what I see, I have my aromatic ring here. I've essentially flipped it along the vertical axis, but you can pick any axis you want for inversion. Okay, so here's our mirror image. Does everyone see how after rotation, so all I did was I rotated my molecule 180 degrees along the vertical axis, just rotated. So here's our original structure. All I did was just rotate the molecule. Just rotation, no flipping of your stereocenters, no modification. Does everyone see how I rotated my molecule to put the hydrogen in the back? Does everyone see that process? So once we've rotated our molecule, now we can look at priority assignments, and now we can assign R and S. So the nitrogen gets the highest priority because nitrogen beats carbon. The carboxylate gets the next highest priority because oxygen beats carbon. And finally, this alkyl chain gets the third priority with the hydrogen being the lowest. I then draw a line going from my highest to lowest priority, and in turn, we would assign this as an S stereocenter, which matches the typical configuration of most amino acids. Does that make sense? Any questions on this example? Any questions on this example? Okay, so the one thing to keep in mind is you'll have to rotate your molecule to place your lowest priority group in the back. But the priority group assignments that I've seen so far look good. Okay, I'd like us now to look at this next example. This time we have two chiral centers at play, and I'd like you to identify each chiral center and then assign the configuration at each chiral center. So this example is a little bit easier than the previous one because you don't have to do as much rotating of your molecule. So let's try to assign the configuration at each stereocenter, and don't be shy to share any questions you have in the chat. And I'd like to see some responses in the chat for the assigned stereochemistry. And don't be shy to share your responses using the annotate feature or using the chat. And I'd be happy to provide feedback. So we have our first proposed assignment that the first center is R. Don't be shy to share your other responses in the chat. Let's try to get the assignments for both stereocenters, and I'd like to see some responses from other members of the class, just so that way we have a pool to have a more nuanced discussion. So we have our first proposed stereochemistry assignment. Let's try to get some responses for the second stereocenter. And for those who would prefer to type in the chat, I'd like to see your proposed stereochemistry assignments in the chat for each of these two stereocenters. Does anyone have a proposal for the stereochemistry for our second stereocenter? As there are two stereocenters, we want to make sure that we've assigned the stereochemistry for each. So we have the second stereocenter tentatively assigned as S. What does the rest of the class think? What are your assignments for these two stereocenters? What does everyone think for these two stereocenters? So we have many students agreeing with these proposed annotations. Does anyone have a different proposed solution? If not, let's discuss this example. So this example is almost pre-primed, so we don't have to do any rotation. The oxygen is the highest priority, followed by the group attached to the amine, followed by the aryl group carbon. We trace from highest to lowest priority, and that would give us an R stereocenter. For our second stereocenter, our amine is the highest priority, followed by the group attached to the oxygen, and followed by our carbon. So tracing from highest to lowest priority, we get the S configuration. So the student responses were perfectly reasonable, and the problem-solving process looked great. Any questions on this example? Any questions on this example? Okay, so let's keep going and let's look at another example. In this case, let's assign and identify each chiral center and assign the configuration at each chiral center. So practice makes perfect. So we have two chiral centers that I'll label A and B. And I'd like you to assign the stereochemistry at each of these two chiral centers. So let's spend about 3 to 4 minutes working on this example, and then we'll come together as a group to discuss. And I really encourage you, as the first step to solving many of these problems, start by making a model of each of these structures. If you make a model, it's much easier to rotate your molecule to place the lowest priority groups in the back. Because I find it's often a little bit tricky to do this on paper or in your head. So you might as well make things as easy and straightforward as possible and use the tools and resources you have at your disposal. So I would recommend utilizing your model kit as part of solving these problems. And don't be shy to share your proposed stereochemistry assignments in the chat. And really, practice does make perfect for these problems. So the more you're able to work through assigning a stereochemistry at different chiral centers, the more comfortable you'll be handling more complicated examples. The one thing that you want to make sure is that the lowest priority group is always in the back. For what's drawn here, could you elaborate a little bit on what you've drawn there? Okay. So we've rotated this molecule. So the lowest priority group was in the back. Okay. And we've assigned stereocenter B as the R configuration. Okay. So let's keep working through this example. Don't be shy to contribute your own stereochemistry assignments in the chat as we work through this example. I'm putting together a model for this molecule to help everyone visualize and understand a little bit about what's going on in this structure. And we'll keep working on this example, and I'd like to see a few stereochemistry assignments for both of our stereocenters before we discuss. So let's keep working on this example, but I'd like to see a few more responses in the chat or verbally before we delve into this example and go over the solution. I really want students to have the opportunity in these sessions to work through the problems and really engage in the problem-solving process. And this is part of the reason why I recommended a model kit at the start of this class, because it does cut down a lot of the extra sort of annoying work that you'd have to do if you're trying to rotate this molecule by hand using drawings. It makes it very intuitive to visualize. So, does anyone have an assignment for the other stereocenters? Does anyone have a proposed assignment for the other two stereocenters in this case, or the other stereocenter in this case? Let's try to get some responses in the chat, and then we'll discuss. What does everyone think for the second stereocenter? What does everyone think for stereocenter A? So we have a proposed assignment that stereocenter A is S. Okay. Does anyone else have a proposed assignment for the stereochemistry for carbons A and B? Does anyone else have a proposed assignment for carbon A and B? Do you agree? Do you disagree? What does everyone think? Let's try to get some responses in the chat, or if you're unsure, let's try to get some questions in the chat. Okay, so let's discuss this example to provide a little bit of guidance here. So we have our proposed assignments of S and R. So let's start by looking at a model of this structure. So here is our complete model of this structure. Let's take it one stereocenter at a time. And let's focus first on this first stereocenter here. The chlorine's pointing towards us. The alkyl group with the bromine is pointing away from us. In terms of priority, the chlorine's the highest, the alkyl bromide's the second highest, the vinyl chloride is the third highest, and this alkyl group is the lowest priority. So what we're going to do is we're going to rotate this whole molecule so that our long chain, that our longest chain is pointing back. And now what we're going to do is we're going to draw what we see. We're just going to draw what we see. So I have my alkyl bromide, I have my chloride, and I have my vinyl chloride. And then in the back, I have the rest of my chain that I'm just going to call R. I'm going to call this entire thing R. Does everyone see how I did that? So here's our initial molecule. Right? Here's our initial molecule. Chlorine is in the front. I'm going to rotate this molecule so that rather than having my vinyl chloride in the back, I'm going to have, so rather than having my vinyl chloride in the back, what I'm going to do is I'm going to rotate this molecule. So now my alkyl chain is in the back. Does everyone see that rotation? Does this make sense to everyone? Can I get some confirmation that everyone understands this first step? So now that we have rotated our molecule, so continuing on, our chloride is the highest priority, our alkyl bromide is the second, or our vinyl chloride is the third. Remember, because bromine has a larger atomic mass than chlorine. So tracing from highest to lowest priority, this is an anti-clockwise or counterclockwise rotation. So this first stereocenter would be S. Does that make sense to everyone? Does everyone understand the logic behind that first step? Okay, so here we go. So we started out with our stereocenter. We're looking at this first stereocenter. The chlorine's pointing out towards us. The alkyl bromide's in the back. We rotated our molecule. So our large alkyl group is in the back, and then we drew what we saw. So this entire giant alkyl chain is in the back. I labeled it as R. From highest to lowest priority, we go from our chlorine to our alkyl bromide to our vinyl chloride. And that in turn gives us a counterclockwise rotation. So we assign the first stereocenter as S. Does that make sense? Does that make sense to everyone? Okay, so now that we have our first center established, let's look at our second stereocenter. So let's look at our second stereocenter. So now we're zeroing in, we're focusing in on the center containing our bromide. Let me correct the model so that way it's fully depicting our structure correctly. Okay, so in this case, in this structure, we have our side chain containing the chloride. We have a hydrogen pointing out of the page towards us, and then we have our bromide in the back. So we can treat this like the following portion of our molecule. And we know how to rotate something like this to place the lowest priority group in the back. So all we have to do is take this molecule and rotate it so hydrogen is in the back. So what we're going to do is we're just going to rotate our carbon-carbon bond so that now our hydrogen is in the back. Now that our hydrogen is in the back, we're just going to draw what we see. Okay, so drawing what we see for this structure, we see that after rotation, we end up with our bromine pointing up, our alkyl chloride on the right, our R group on the left, and our hydrogen in the back. Does everyone see that? Does everyone see how the hydrogen's now in the back? Does everyone see how the hydrogen's now in the back? Okay, so now that we have that established, we can rank our groups in order of priority. So we know the bromine gets the highest priority. the alkyl chloride gets the second. This long chain alkyl group is the third priority. Hydrogen's the fourth. So now that we have our priority rankings, we simply trace from the highest to lowest priority, and that in turn is a clockwise rotation. So the second stereocenter will be R. Does that make sense to everyone? Does that make sense? So another way that you can think about rotation is really that you're just changing your viewpoint. You're just changing your perspective on the molecule. So for example, to get this first rotation, all we did is we're simply looking at the molecule from this angle. We're looking at the molecule from the opposite side to our lowest priority group. And that in turn gives us, if we're looking just from a straight on perspective, that would give us the following motif. So you can think a lot about how do I view my molecule, from what perspective, in order to place the lowest priority group in the back. You can think of it a lot like the way that you view molecules to make Newman projections. And in that case, looking at our priority assignments, we then just note whether we're going clockwise or counterclockwise. Does that alternative explanation help in terms of helping us visualize and view molecules from different perspectives to place the lowest priority group in the back? This is really something where I encourage you to make the model and just keep working on examples, because this kind of three-dimensional reasoning is a skill that, if you continue to hone and develop, will be very useful as you continue on with organic. So just to show you this, the same perspective here. So what we're going to do, if hydrogen's the lowest priority, we're going to look at this molecule from the opposite perspective, from the opposite side. And that in turn gives us a molecule where the chloride's on the right, the R group, the chloride's on the left, the R group's on the right, and the bromine's pointing down. So let's look at the model kit again for the second stereocenter, just to be sure that we have this completely assigned. Okay, so we have our bromide. There we go. So we have our bromide. Looking at the stereochemistry for our bromide, the bromine is pointing away from us currently. So we rotated our molecule, and now we draw what we see now that our hydrogen is pointing away from us. That gave us the following depiction. Okay, perfect. And that's why we assign the center as R. So from another perspective, if we're trying to alter our view, if we're trying to take this molecule and rotate our molecule so that now the hydrogen is in the back, another way that you can think about it is just like Newman projections, we're going to view our molecule from the opposite perspective. And that in turn, we can write this molecule like this. And then rewrite via rotation So let's showcase this alternative view using our model kit. So in this case, here's our initial model. So now what we're going to do is, let me just make sure the view is exactly matched up. Here we go. So here's our initial view. And now what we're going to do is we're going to look at the molecule from the opposite perspective. We're going to look at the molecule from the opposite perspective, and then we're just going to draw what we see after viewing the molecule from the opposite side. So in this case, if our hydrogen is now placed in the back, we have our bromine, we have our alkyl chain, and then we have our alkyl chloride with our hydrogen in the back. So tracing from the highest to lowest priority, that in turn gives us an R configuration. Does everyone see that? How we just viewed the molecule from the opposite side? Okay, so those are two ways of thinking about it. If you're good at visualizing molecules from the perspective of Newman projections and just thinking, okay, what bond am I looking down when I'm drawing a Newman-like projection, then you can use that same logic to view your molecule from a perspective where your lowest priority group is in the back. Does this example make sense? Does this example make sense? Again, highly encourage you to use your model kit. Okay, so let's look at another very biologically relevant molecule, this time with 3 stereocenters. And I'll label these as A, B, and C. And remember our tricks for rotating a molecule and our tools to rotate a molecule. And your goal is to assign the stereocenter and configuration at each of these 3 stereocenters. This molecule is quite relevant in biological settings. Would someone like to propose? Does anyone know the name for this common biomolecule? Does anyone know the name for this common biomolecule by chance? If not, you may want to take this structure and after class, look up this structure and see what the name is. This pops up a lot in biology. It's a pretty commonly mentioned structure and molecule. Anyway, what I'd like you to do over the next 5 to 6 minutes is to assign the stereochemistry at each of these 3 stereocenters. You may want to rotate your molecule first so that your lowest priority groups are in the back. And I find it's often easier to visualize and complete these rotations when you have a model kit ready to go. So let's work on this example over 5 to 6 minutes. Don't be shy to use the annotate tool or to share a picture in the chat. And if possible, I'd like students as well to share their assigned configurations for each of these 3 stereocenters before we discuss. And I want at least 2 to 3 student responses before we continue on and we discuss this example. It's better to attempt the example and then revise your logic after viewing the solution rather than just waiting for the solution. I find a lot of the learning in terms of the mechanics for this process comes from attempting the problem, struggling with the problem, and then identifying parts of your logic or reasoning that need to be modified and identifying parts of your logic and reasoning that were perfectly correct as well. So I'm making a model of this structure now. That's often the first step that I take when I'm solving these problems. And once you do a lot of these problems, you'll eventually get to the point where you may not need a model kit. But that doesn't mean it's not useful to have necessarily. And don't be shy to share any questions that you have and any proposed stereochemistry assignments and configuration assignments that you have in the chat. For those who are curious, this molecule is known as biotin. So we have a proposed assignment that Stereocenter C, is that R or S? Sorry, it looks like we have this assigned as S. Okay. Let's try to get assignments for the other stereocenters, and I'd like to see some other students contributing to this discussion with their proposed stereochemistry assignments. Note, I'm about getting everything perfect the first time. I mainly want to see the logic that you're using so that way I can provide feedback, and I want you to practice the mechanics of taking a molecule and rotating skill that is best learned via practice. So let's keep working on this example. And I'd like to see students sharing their proposed assignment for our other 2 stereocenters. And does anyone have another stereochemical assignment for any of these stereocenters? And don't worry necessarily if your response disagrees with your classmates. We just want to have a pool of responses so we can look at different ways that students approach the problem and discuss different aspects of solving these Iupac stereochemistry problems. So we have for Stereocenter A, after rotation, the center was assigned as having an R configuration. Looks reasonable so far. Let's try to get assignments for the remaining stereocenters, and then we'll discuss. And really, for other students in the class, don't be shy to contribute your own stereochemical assignments using the annotate tool or in the chat. And if you have any questions, if you're unsure about any of these examples, don't be shy to ask. I'd be happy to explain any part of this example, or if there's a part that you're stuck on getting started, I'd be happy to go over it and explain how to start these problems. So we have assignments for stereocenters A and C. Would someone like to provide a proposed stereocenter assignment for B, stereocenter B? This is an example that's pretty similar to what you'd get on an exam in terms of difficulty. So you want to make sure you're comfortable handling stereochemical assignment for molecules such as this, which require rotation. So we have a rotated version of, and we've rotated our view of stereocenter B, and in turn, that led to a proposed assignment for our stereocenter as an S stereocenter. Okay, perfect, perfect. So does anyone else have another assignment? Do you agree with these proposed assignments and drawings? Do you disagree? What does everyone think? Let's try to get some responses in the chat. Does everyone agree with these proposed responses? Do your proposed assignments look the same? Are there any cases where your assignments are different? Does everyone agree with these proposals so far? Okay, so let's clear these annotations and let's discuss this example. Okay, so first things first, I made a model, okay? It's always the first step in this process. Okay, so here is let me rotate it so it's more visible. The camera does really odd things when I hold the structure up to the camera, so sometimes I have to correct it after I notice the camera has flipped something around. Okay, so here is our proposed structure. Here is our structure and our initial view of this molecule, known as biotin. For those who are biology majors, this is a pretty common structure that you'll see. Okay, so let's start with the topmost stereocenter A. So currently we have our hydrogen in the front, right? Now, what I'm going to do is I'm going to take this whole molecule and I'm going to flip it. I'm going to rotate my entire molecule, almost like flipping a pancake. I'm going to rotate my entire molecule 180 degrees on the vertical axis. So I'm going to flip this entire molecule 180 degrees. And now I'm just going to draw what I see. So I have flipped my molecule over, almost like flipping a pancake. And now I'm going to draw what I see. The reason why I'm doing this is because rather than having to worry about dealing with every single stereocenter and rotating every single stereocenter at once, I notice I have a bunch of cases where I have a hydrogen in the front and I want all of my hydrogens to be in the back. So I flip this entire molecule 180 degrees, like flipping a pancake. So we start off with this, and I flip my molecule 180 degrees. Does everyone see that? Does everyone see how I rotated the molecule? Okay, so now as a result, this alkyl group is now, rather than being on the bottom side, it's now on the top side, and it's pointing towards us. 1, 2, 3, 4. Okay, so here's our redrawn molecule. Here's our redrawn molecule. And now this makes it really easy for us to assign priority. So looking at this, at our redrawn molecule, we now have a pretty easy track to assigning priority and assigning stereochemistry because all of our lower priority groups are now in the back. So this is an efficient time-saving process where if you strategically rotate your entire molecule, you can often set it up so many of your problematic low priority stereocenters are in the back. Now, looking at stereocenter A, I'm going to assign priority now. So we're going to assign priority now. So the nitrogen's the highest priority, followed by the carbon attached to the sulfur, followed by the carbon attached to the nitrogen. So tracing from highest to lowest priority, for stereocenter A, I get the R configuration. Oh, sorry, this is not stereocenter A, this is stereocenter B. Just to show the mapping, these two centers are the same. Does that assignment make sense? So this first assignment will be R here. Oh, oops, highest to lowest, counterclockwise, so that would be S. There we go. So we have our first stereocenter assignment. Now let's look at Stereocenter A. And Stereocenter A, after we flipped our molecule, is down here. So now assigning priority for Stereocenter A, we have our nitrogen, followed by our carbon attached to the sulfur, followed by our carbon attached to the nitrogen. Going from highest to lowest priority, we have a clockwise rotation, and that gives us an assignment of R. So Stereocenter A would be an R configuration. Finally, looking at Stereocenter C, we rank our groups from highest to lowest priority. So in this case, our sulfur gets the highest priority, followed by our carbon attached to the nitrogen, followed by this long chain. Tracing, we have a counterclockwise rotation, and that gives us an S configuration. Does this example make sense? Do these assignments make sense? The only thing that's a little bit tricky when you flip your whole molecule is that you need to make sure you properly label your carbons. One trick that I like to use is I like to put a unique color around one of my carbons, and I always make sure that I know where that carbon is. Does this example make sense to everyone? So just to recap the entire logical process from start to finish. Okay, so we start off with our molecule looking like this. The hydrogens are pointing towards us. I have taken my molecule and rotated it 180 degrees to get the following structure. That's what I drew here. My hydrogens are now in the back. This alkyl group is now up top and pointing towards us. Now that I have my structure drawn, I assign priority. In this case, for the first top stereocenter, which is B after rotation, we have our nitrogen, followed by our carbon attached to the sulfur, followed by our carbon attached to the nitrogen. That gives a counterclockwise rotation, which would be S. For Stereocenter A, our nitrogen is the highest priority, carbon attached to the sulfur, followed by the carbon attached to the nitrogen. That rotation gives us a clockwise rotation from highest to lowest priority, and that gives us an R stereocenter. For our last alkyl chain, our sulfur is the highest priority, followed by our carbon attached to the nitrogen, followed by the alkyl chain. Tracing counterclockwise from highest to lowest priority implies we have an S stereochemistry. So the student proposed stereochemical assignments were perfectly correct. Any questions on this example? Does this example make sense? One thing that is really important to not get confused on is that when you flip your molecule, when you rotate your molecule, make sure that you know what carbon you're referring to, what atom you're referring to after rotation. Does that make sense? Perfect. So, what I'd like everyone to do is, I think this is a good stopping point for this supplemental lecture. What I want everyone to do during the weekend is I have some homework on stereochemistry and stereochemical assignment. And I would like you to work on additional homework problems in your book and go over the problems in the notes one more time. And you can even, and this is really cool, if you open up Marvin Sketch, for those who have downloaded Marvin Sketch allows you, whatever structure you draw in Marvin Sketch, it can actually tell you the stereochemistry. So one thing that I used to do for practice is I would open up ChemDraw when I was a student, which is just like Marvin Sketch. I would draw the structure out, just a random structure, and then I would try to assign the stereochemistry on my own, and then I would have the computer tell me the stereochemistry, and then I'd compare my answer. I really encourage you to really practice with this, because an example like this is of reasonable difficulty for your exam. So you need to be able to handle assigning a stereochemistry at different chiral centers. And we're going to need to have this completely understood, or really well understood, for the next sequence of lectures, because the stereochemistry is important for assigning both enantiomers and diastereoisomers. Does everyone understand sort of what I'd want everyone to do before next lecture? Just work on some additional practice, work on using your model kit. If you haven't gotten a model kit already, I would recommend ordering one using the link, because stereochemistry is something that will stay with us all the way until the end of Organic 2. And you can do everything by hand, but a model kit is so much easier in terms of visualizing these rotations. So I'll be pausing the lecture recording